there. So today we are going to talk about modeling again, but this time with more predictors. So that kind of actually resembles what we do in the real world. But anyway, that's where we're going. So let's not dive in because I use that one too much. And let's just get started. Okay, linear models with multiple predictors. My hope is that this is all review so that, frankly, so that I don't have to go into as depth and effectively replicate what you've learned in the multivariate stats class. But, yeah, sorry, I realize that's not a complete sentence. This is not a substitute for a full regression class. It's just enough to get you dangerous with tidy models. Okay, so we're going to play with a little bit of a different data set for a moment, just before we go back to the Parisian art auctions. So the Allbacks data frame gives measurements on the volume and weight of 15 books, some of which are paperback, some of which are hardback, and they give us a nice tiny little table with volume in cubic centimeters, because this is an Australian data set, area in square centimeters, and weight in grams. Ta-da! And there's a cover factor of HB, which is hardback, or PB, which is probably not peanut butter. Okay, so using our nice tidy little data, we're gonna use a linear regression and keep trying and playing around with tidy models. So with linear regression, we're gonna pipe that into our set engine, and in turn pipe that into our fitting. So here we've indicated weight is our outcome, and then we have the little tilde, and that is modeled as a function of volume. And we're using the data as Allbacks. Then we're going to tidy it all up. That is exactly what is happening in the code. We can see we have a nice plot, and we've got a nice tibble that spits out enough information to get us started with regression, at least from a descriptive standpoint. Whether this model adequately explains our data, if it's better than an intercept-only model, that I'll leave as an exercise to the reader. Okay, so here our intercept is effectively the expected weight when volume is 0. No. Yes. And I think apparently I don't break that down. Okay, so here we have expected weight as a function of volume. So 1 unit increase in volume is associated with a 0.71 unit increase in weight. And at 0 volume, we expect our book to weigh 108 grams. So obviously we need to put something else in here, right? Because there's more information. So here in this model, I have added a second predictor. All I've done is put in plus cover. So now we have a second factor. So the average weight with 0 volume and a hardcover is 198 grams. But if we happen to have a soft cover, so a paperback cover, in order to get what the intercept would be for that group, we can just subtract. So 198 minus 184, so like 12 grams. It's tiny. So, apparently I was supposed to save the estimate interpretation. Oops. So here is our final estimate interpretation. Slope for volume, all else held constant, so all else being equal, for every additional cubic centimeter books are larger in volume, we would expect the weight to be higher on average by 0.72 grams. You'll notice that this language is not causal, it's not predictive, it's descriptive. And that's because we are using the model to describe our data. We're not making predictions, we are not extrapolating, we are not making any causal statements or confirmatory statements. And so in that sense, given that this is an exploratory analysis with no goal of prediction or clear hypotheses, then we can just focus on the coefficients. Now the cover is all else held constant. Paperback books weigh on average 184 grams less than hardcover books. And our intercept is hardcover books with 0 volume are expected to weigh 198 grams on average. Does this make any sense in context? No. That is the kind of the fundamental weakness of the intercept when you don't center your data at all. So here the intercept is not particularly useful, but it is what it is. So what if we're interested in predicting the weight of books from their volume and cover type? Do you think a model with main effects or an interaction effect would be more appropriate? Audience participation points, except this is asynchronous, so anyway, so think about it. I have my thoughts and you'll hear them soon, but feel free to pause and collect your thoughts, because it's good to develop your statistical intuition. Right, so here's my hint. So the main effects mean that the rate at which the weight changes as volume increases would be the same for hardback and paperback books. And an interaction effect would mean that the rate at which the weight changes would be different as a function of volume for hardback versus paperback books. Here are our plots from our data. I'm going to keep this running apparently and grab 4 books to illustrate why this interaction is probably not necessary here. Yes, I forgot to bring the props when I started filming. So yeah, books. Cover, surface area, pretty much the same. Because some books, there is an upper limit. Like this one is really heavy because it has a reinforced binder that I don't think you can see. But it adds a little extra, but not a ton. We would need a way bigger data set in order to detect these effects. Like my novelty dictionary that I bring and drop for every time I teach personality on the lexical hypothesis. You won't get to experience the full effect, but I'm going to do it anyway. Fun. That is going to be great audio for never. So here, when we look at our data, we can see that technically there's an interaction. Maybe. Yeah. So main effects means that we have parallel slopes, that they don't matter, that the growth is the same, versus interaction effects where you can have non-parallel slopes. And so if, as the book got bigger, it might get heavier, we could see that, but not in this data set. This data set is too small and it's just normal books. not weird prop books. So yeah, often when we model, one of the things that we really try and do is pick the simplest model. So if we have a ton of different models and they all predict equally well, then we pick the one in general with fewer assumptions. And that's not always the case. There is a variety of trade-offs to make, whether you want to include more predictors at trading off between complexity and parsimony. But the general idea is that you only add more variables to your model if the addition of that variable brings something valuable in terms of predictive power, or valuable in another sense. Like it is useful to demonstrate that such an effect does not add predictive power. So model selection can actually have a bit of a rhetorical purpose if your goal is to demonstrate that something does not have an effect when you control for other things. Then it can be useful to include in. But in general, the idea is that the simplest model is best, the parsimonious model. Again, I imagine that you've covered this in much greater detail with Mike and Eric, so I won't belabor the point. But for the most part, simpler tends to be better. And yeah. Okay, so visually, which of these models is preferable? You'll notice I haven't pronounced this name because I have tried a lot outside of the context of this video, but it's not happening. So, which is preferable? Well, spoilers, the model with less complexity. So the one without the interaction. Because sure, it's not like we have a nice science crossover effect. We have parallel lines. And one with the effect, just a little. It's not even clear when they would cross. I think they would cross when you get into negative volume. So not very helpful. Okay, so how do we pick beyond just the eyeball test? Well, we can see with the proportion of variance explained. So just like a correlation, you can square it to see how much of the variance you've explained in the association. You can do that with an entire regression. And that's what R-squared is. It's effectively explaining the variability, or is the percentage of variability in the response variable that is explained by the entire regression model. And that R is big multiple R. And we've just squared it to make it comparable in terms of interpretation. So when we take a quick glance at our model, we can see that the R-squared is almost 93%, versus in the interaction model, it's almost 93%. Yeah, it doesn't differ until the third decimal place. And I can tell you, given the sample size, even with this high amount of variance, the marginal effects are not going to be there. This difference is probably not significant. So clear, but still, the model with more terms does have a higher R-squared, just by how the R-squared method works. It's literally capturing any association whatsoever, even if it's itty-bitty. At worst, those models will be comparable. At minimum, adding another parameter doesn't take away variance. It can only have a zero or positive effect, which is not particularly useful because our goal is to model simplicity. And this raw R-squared does not have any kind of penalty or incentive structure to not put in every variable, which is effectively what machine learning is. So I think I already said this. So for models, for R-squared for model selection with multiple explanatory variables, it is not a good idea to base your entire decision on that difference. So we use we should be using adjusted R-squared. Adjusted R-squared doesn't increase if a new variable doesn't provide any new information. Effectively, it has a penalty built in for the number of additional parameters. So, and the adjusted R-squared penalty is pretty good. You can actually, if you tinker around with it, you can get a negative adjusted R-squared, which I think is kind of fun. But in theory, that's impossible. But in practice, it is. Cool. So in general, there tends to be an adjusted penalty for adding in, as we can see here, comparing the two R-squareds, where we have 92.7 versus 92.9. So that's with the unadjusted R-squared versus the adjusted R-squared, where our adjusted R-squared penalty is small. It's 91.5 versus 91.05. So we can see here that there is not a benefit. If anything, there's a net cost to adding this extra parameter because it doesn't explain additional variance. Part of that is we have a tiny data set, but I belabor the point. Adjusted R-squared tends to be more useful when you are trying to make decisions with the parsimony versus complexity trade-off. And we can just test this out if we want using a cutesy little logic component of, is the R-squared in the interaction model bigger than the R-squared in the main effects model? Yes, but does it still hold with adjusted? No, it does not. Woo! Which I realize that you could all see from this eyeball test, but you can have R do that for you. So that is wrapping up. So I'll see you in a bit. Bye-bye. Okay, bye-bye.